lab today, let's meet upstairs. Upstairs. Okay guys, good morning. Let's get started. First off, any questions about the material? Test on Monday, typical format, nomenclature of the dienes, and then all the topics, starting from reactions of dienes, Diels-Alder, what we got, mass spec, resonance, substitution elimination reactions. I cover everything? Everything that we've covered, yeah? Spectroscopy will be the mass spec. There will be mechanisms, there'll be predictive products, etc. Very similar to the first two tests. Very similar to type of questions in the workbook. Any questions about the test on Monday? Questions about the material? So y'all ready? Ready for test on Monday? No questions? If there's no questions, James?
Like if you're doing a SN2 reaction and you do life-size back, what if the atom that you show has stereochemistry and also the nucleophile stereochemistry? Would only the electron change stereochemistry? You know what I'm saying?
Correct. You only do inversion at backside attack carbons and backside attack carbons.
So the nucleophile stereochemistry sticks in.
That's correct. Because you're not doing any backside attack of the nucleophile carbon. You're not breaking any bonds at the nucleophile carbon, right? Usually in the nucleophile. So you're not breaking any bonds. You're not changing. Not changing the stereochemistry. Any other questions about the material? Well, if there's no questions, we're going to move ahead to new material. This will not be on the test, but it will be on the final exam. Two topics. I gave you handout on radical bromination and also on UV vis. UV vis had the picture of the carrot. Okay, radical bromination is a very important reaction of alkanes. Alkanes. Typically alkanes, we've never said they had any reactivity. They don't have a pi bond and they don't have a lone pair. So how can they be nucleophilic? How can they attack electrophile or be attacked or anything? Alkanes will react with halogens, and the most common is bromine because of the thermodynamics, and we'll mention why. But you can react such an alkane with just elemental bromine. It does require a light or peroxide. So H nu would be your equation for light energy, or you can just heat. But usually you include some type of light energy or a peroxide. And we can actually get a brominated product. The bromine will be here on the tertiary carbon. We'll say why. It's very analogous to tertiary carbocation. And we look at what would be the byproduct here. If we show up a reaction where all products are shown, what would be the byproduct? Somebody said it. Yeah, HBr. Suppose there's two bromines here, okay? And if we look at this molecule here, there's an H here, there's a tertiary hydrogen there, and that H is now gone. So overall, this is a substitution reaction because the bromine has substituted the H. Okay, and we produce HBr as a byproduct. So you can do substitution reactions with alkanes with halogens. This is a radical reaction. We'll look at it. But first we can compare it to the alkene reaction, because if you're reacting alkene with elemental bromine, we all know that what you get is an addition reaction, and you get the dibromide. And if we add some precise stereochemistry, we could show that in terms of relative. We know that's not chiral, we know that's chiral, that's going to be a racemic mixture. But there's no like meso because that requires you to have two chiral carbons. So that's an addition reaction. We're just adding the bromine here, and there's no byproduct. Okay, that's good old alkene chemistry. But this is the new alkane reacting with bromine. It's a radical reaction. Let's look at the mechanism. The first step of the mechanism is you put some type of energy into bromine, and this bond will homolytically rupture or break. Okay? The electrons, we're going to move one electron. Okay, there's lone pairs here, yeah? We're going to move one electron this way, and we're using a Fish-Hook arrow, right? Whenever we do radicals, it's just Fish-Hook, and we're going to move the other electron here. This is going to give a bromine with 3 lone pairs, and then what else is there? What does this arrow mean?
1 electron.
1 electron sitting here. Now, it gives a repeat over here, but instead of drawing it, a repeat, I'm just going to say 2 of these. And this is some type of energy, okay, which can be light or heat to cause this. But it can, or peroxide. Now, with the peroxide, I don't think we have time to get into how that causes this to form radicals. Basically, what do we do here? We form bromine radicals. What's a radical? Something with a single unpaired electron. What's the charge of this species? It's neutral. Okay, it's no charge. It's a neutral atom. It's a radical. We're not going to say how peroxide causes this, but just know that peroxide can do this. Because peroxide, briefly with heat, peroxides themselves form radicals, and then that radical can make this become a radical. We may look at it a little bit later, but okay. And light is a common way to do this. Sometimes light is more efficient in doing this than just heat. Okay, so that would be here. So bromine radicals, that's the first thing we want to form here. This is called homolytic bond cleavage. As opposed to heterolytic. All right? If you take HBr and put it in water, what will happen to this bond? The 2 electrons will move here, and you will get H plus and Br. Well, we're moving both electrons here, and that's minus. This is called heterolytic bond cleavage. The homo meaning same is like each atom gets sort of the same outcome. Each atom gets 1 electron. But over here, each atom did not get 1 electron. The bromine got them both. So that was different outcome for each, or different. It's called heterolytic bond cleavage. It's called homolytic bond cleavage. Promoted or caused by the light or the heat or peroxide. We get bromine radicals. Once we get bromine radicals, then we can start doing our reaction up here. You can redraw that here if you want, the same molecule. I'm going to just take it from here. I erase the H. Okay, bromine radical. This thing will actually kind of strip. That's not a good chemistry term, but it will or extract. That's maybe a little bit better. A hydrogen radical. Basically, we can say this electron will team up with one of these electrons. The other electron in the bond will stay behind on the carbon. What does that arrow movement give? Now, I'm not showing a transition state and talking about how this occurs. We often don't. Okay, we just sort of say this is how it happens. All right. But if we take one of these electrons, team it up here, and that electron stays with the nucleus, what do we form? What's now on this carbon here, according to my arrow movement? A radical. And what did we make? There. We got an H with one electron, and we got a bromine with 3 lone pairs, and we're saying that one electron teamed up with this one, so let's team them up. But what do we have here between the H and Br now? We got a bond. That's HBr. When the 2 electrons teamed up, we made a covalent bond. Again, there's always questions you can ask for. Why? How? Well, we could go on, and you have the bonding here, it's a book that thick. But we're showing some basic mechanistic thought here, as opposed to just saying, hey, guess what? This is magic, and let's just memorize an outcome. I'm trying to rationalize the outcome to a degree. Okay. Well, question, why did I abstract that H and make radical there? Why didn't I abstract one over here and make radical here? Well, what type of carbon did I make radical on?
Tertiary.
Tertiary. Is that better, or would you rather make a primary radical? Oh, we know cations are better on tertiary. Why is a radical better on tertiary? For the same reason as cations, because a radical is electron poor. Does that carbon have an octet? How many electrons does that carbon own? Oh, we don't need to say own. How many electrons in terms of octet count? 7. It does not have an octet. 7 is not 8. So it's electron poor. It's electron poor just like a cation. It's not as electron poor as a cation, but it's still electron poor. Thus, it's still stabilized by donation like a cation. A radical is stabilized just like a cation. And thus, you want radicals are best on tertiary carbons. We'll also be able to do resonance of radicals. This is your best radical. So we have some selectivity here. So the tertiary radical is preferred. Now, how can we get to final product? We already formed the HBr. How can we get to the other product, the main organic product?
Other BR, Angela.
Tell me again.
The other BR.
You said other Br, okay, because we had 2 of these. One of them attracted the H. You want the other one to then team up with this electron. Tag team bond formation. What would that give?
Covalent bond.
Boom, boom, boom. Boom. Now we have a bromine. That's 2 electrons. One came from bromine, one came from the radical. They teamed up to make a bond. Now we formed our 2 products, right? Okay, a couple of things to say about this. How we're going to go ahead and say the main thing. First off, that's not how we get final product. Because, or that's not the correct mechanism, because a mechanism has to account for more than just forming products. For example, it has to account for forming product, but it also has to account for like stereochemistry of the product. For example, what if our mechanism shows inversion, our product shows inversion, but our mechanism doesn't explain that? And actually our mechanism maybe suggests that it should be racemic. Then possibly your mechanism is not correct. There's more things than just that outcome. Here's another piece of information that we know about this reaction. If you use light, you actually only have to shine the light at the very beginning for a little bit. Then you can turn the light off and the reaction will keep going. It will keep going without the light. Now, how does that happen? Why does it do that? Why does it keep going without the light? And does our mechanism indicate why that happens? For example, if we use the other bromine here, if we use one to abstract the H and one to then bond, that means this is gone, right? We use these up. How are we going to make more bromine radicals?
Shine more light.
Now you could say that little bit of light makes them all become bromine radicals and it takes off. But no, what actually happens is you can tell that all the bromine radicals are not consumed because of color. Or all the bromine is not consumed. If we use up all the bromine radicals, one here and one here, then we would have to cleave another bromine molecule and create more bromine radicals. Well, how are you going to do that? Light. What if the light's turned off? Is this going to cleave? Theoretically, no. Because if it does keep cleaving, why would we need light to begin with? So how can we explain the fact that we only need the light at the beginning and then the reaction just sort of keeps going on its own? Well, this is how. Because at this point, I'll move down here. Here's what we need to do. We need to generate bromine radicals without light. Because apparently that's what happens in the reaction. The bromine radicals are then generated without light. Here's how they can be generated. Instead of one of your bromine radicals reacting here, what if this electron just teams up with one of these? And this other electron goes here. What does this arrow movement give? Electron teaming up with one electron of the bromine, what does that give?
Same bond.
That gives product. It gives product, but what do we also generate?
Another radical.
We generate bromine radicals. Since we generate bromine radicals, we don't need the light anymore. We can turn the light off. Now the bromine radical, now we have a cycle. Now this can come up here. That bromine radical can then repeat the process. It can extract an H. From a new molecule of alkane, we get the radical. Now we come in with a new bromine. The light's off now. This subtracts an H, a bromine. We make the bromine bond, but we create a new radical. And then you do this just over and over. Now we have a cycle, and we don't need the light anymore. And this is called propagation. The reaction is propagated or continued. And this is indeed more of the proposed in the mechanism that is usually shown for this. And that would hopefully explain why you only need the light at the very beginning to kind of kickstart it, and then it propagates itself. It keeps going by generating bromine radicals this way. Okay, reason for regioselectivity. Why do we get the bromine bonded there? Well, we've kind of already explained that, because that's where the radical is going to be. And why is the radical going to be there? Because we made it that that's going to be the most stable radical. that radical will be more stable than having a radical out here, just like a cation would be more stable there than a cation here. Okay? Inductive donation, right? Electron poor radical stabilized by inductive donation. Now, of course, this down here is a very different reaction, right? There's no radical here. Here the pi bond attacks the bromine, and then you have a bromonium ion after the back bonding. This is an ionic mechanism. All your intermediates here are ions. It's actually only one intermediate. It's bromonium, but you also have the bromide, which attacks the bromonium. Ionic mechanism. This is the radical mechanism. All your intermediates are radicals. We never made any ions, did we? There's no ions. There's no charged species. They're radicals. Okay. So, show the product in that first reaction down there. Hopefully pretty straightforward once you figure out what's going on. How we do? And what else did we make here? Plus what? What's HBr? Now we actually were scheduled to do this type of reaction in lab this week. Said we delayed because 2 weeks ago we had a review session. Okay? So we didn't do the lab and we didn't have an extra lab report. I know you're kind of miffed about that. But when you do this reaction, you can look, and the one in the lab, actually it's not in the lab book, I have to hand it out. I don't think it's in the lab book. But it's actually a dibromination. HBr is important. You can do this reaction and you actually add it up, you turn the light on, and then after a few minutes, actually vapor will start coming out. Gas. It's HBr. Okay? What about solvent? What solvent would you use for this reaction? Solvent would you want to use for this reaction? We introduced solvents week 1. I gave you a list of solvents. Hopefully you've been looking at that list and seeing what type of solvents we've been using in lab. If I have a proposed solvent for this reaction, I'm not showing one. Okay, down here, how about this? Any questions about that product? Down here. Down here I'm showing, that's a peroxide. Now it's not hydrogen peroxide. Hydrogen peroxide would be H2O2. Of course, peroxide is where you have oxygens bonded together. And you put H's on each end, and you got hydrogen peroxide. This is, okay, it's condensed. We got exactly the 2 oxygens. Now on each oxygen is one of these. And that is a carbonyl with a benzene ring. Carbonyl with a benzene ring. So it's still got the peroxide, it's just instead of H's, it's got these benzoyl groups. So what is the name of this compound? Not hydrogen groups, not hydrogen peroxide, it's got benzyl groups, so it's
Benzyl peroxide.
benzyl peroxide. Anybody ever heard that? No? Where's benzyl peroxide found at? Acne medication? Yeah. Uh-huh. Yeah, it's peroxide. Peroxides will form radicals. They'll homolytically cleave in the presence of light and stuff. And then those radicals will kill the bacteria. Up there we showed it. Peroxides are used because they may form radicals easier, but once this forms a radical, don't write this down, but just trying to give you an idea. We get this radical, then this can join up here, and we can produce bromine radicals. And so it can sort of serve to form your bromine radicals. So peroxides are sometimes used as an alternative to light or heat. And a common one is instead of hydrogen peroxide, which is aqueous, because this cannot be pure or it'll explode. Many of these cannot either, but at least they're not wet. They're more organic. Because of the organic nature, they'll dissolve easier in organic solvents, especially the type that solvents you would use for this reaction. So that's benzoyl peroxide. You need to be able to recognize that. It may also be written like this sometimes, benzoyl, maybe something like that, because these are benzoyl groups. It's just a common peroxide. So, you see bromine and peroxide radical chemistry. Okay, radical. The question becomes here, where's the best place to make a radical? Well, it's the same as cation. Where's the best place to make a cation?
Tertiary.
There's no tertiary
Secondary.
carbon here.
Secondary.
And that's strict, I reckon that's a tertiary carbon, but usually the primary, secondary, tertiary is only applied to tetrahedral carbons. You don't really classify these. All these out here are as secondary, primary.
So the secondary difference.
Benzylic. Benzylic cation, very good. Yeah. Same thing here. We're going to get radical formed here preferentially. And basically, after sort of assessing what's going on here, we can come to a conclusion that's we're going to get we can call that benzylic bromination, because we brominated at the benzylic position. Same mechanism as above, we'd make radical here and it would capture the bromine from the Br2. Benzylic bromination is a very common reaction because it's quite selective here. Now I'll go ahead and say that when I mention selectivity. Typically you only see bromine used in these radical reactions. Why not chlorine? Why not iodine? Why not chlorine? Well, it's largely based on the thermodynamics. The bromination just turns out to be very good, favorable thermodynamics. For example, if you do this reaction with iodine, and you do some calculations like we learned how to do, it's actually endothermic with iodine. And this can be an equilibrium reaction because this can sort of reform radicals and they can go backwards. So it's driven by thermodynamics. If you do this with iodine, it's endothermic, and so actually this is favored. And actually a lot of iodine compounds, they're not stable. They'll go back this way. So the iodine just doesn't work out. It's not thermodynamically favored. Chlorine, on the other hand, It's too favored. It's too exothermic. And this has to do with the bond strengths. The smaller the halogen, the stronger the bond. Big iodine, it's a weaker bond. With chlorine, it's so exothermic that you lose the selectivity. If you react this with chlorine, it'll chlorinate here, here, and here. And you'll get mixtures that you can't do anything with. You can't purify. You'll say, why does it chlorinate here? I thought that was a better radical. Well, it is, but it's so exothermic that it loses its selectivity. That's like if water is running down the hill or down the road and it comes and it can go down this road here or it can go up this road. Which one's it going to go? It's going to go down. Well, yeah, if it's only a little bit of water. What if it's a hurricane? Which way is the water going to go? They go both ways because there's just so much water, it's going to lose its selectivity. There's just so much energy there with chlorine, it's not going to care that that's a better radical. Now with fluorine, it's so exothermic you better stand back because fluorine will react to that explosively and you'll be in trouble. So it turns out that Mother Nature just gave us bromine that's got good thermodynamics, that's safe enough to do, you know, in a lab, and thus people do it. You know, reactions that are so dangerous, nobody does them, so they're not that useful. So it's very useful. Sometimes you see chlorination, but it has to be very controlled and safe. And fluorination is just not a synthetically useful reaction because it's so exothermic and so dangerous. Maybe you can do it on a very small scale, or some specialized labs do it. Iodine is, there's no hope for that. A lot of iodine compounds will actually, they'll be stored over some type of radical inhibitor. Because if it starts forming radicals, it'll just go backwards. So you find an iodine compound, it may be stored over like copper metal or something. And the copper metal inhibits radical formation, so it won't start going backwards. Okay, down here, what is NBS? N-bromosuccinimide. It's a source of bromine radicals. I'm not going to tell you anything more than that. But this bromine-nitrogen bond will homolytically cleave under the right condition, and you can produce bromine radicals. Okay? If that was an H, that would just be succinimide. This is N-bromosuccinimide. Bromine radicals like to form the bromine radicals. Where are we going to make radical at? Where's the best place to make radical? Actually, right here. Why is that the best place? It's actually going to be resonance stabilized. Okay? P orbital, P orbital. That's going to be P orbital with one electron in the P orbital. 3 P orbitals lined up. But in terms of just drawing your resonance structures, we can do that. Because one of these electrons can move here and team up with that one and make pi bond between the 2 carbons. The other electron can move out here. And that's actually going to be a resonance structure. What will it look like? Go ahead and draw it. Just follow my arrows and that'll help you draw the resonance structure. So I made electron-electron teaming up here to make pi bond. I moved the other one out here, and so we have that. That's a resonance structure, because what's the definition of a resonance structure? It's just an alternative Lewis structure where all we moved is pi electrons. Everybody agree that this is an alternative Lewis structure? Now, did we move any atoms? No. If we did, it wouldn't be a resonance structure. It would be a new compound. All we did was move pi electrons. Now this assumes that this electron is in a p orbital, and it's probably going to be because that's actually, you could question that. How many electron regions around this carbon? Well, how many H's are here? Originally there were how many?
2.
2. To form the radical, how many H's were abstracted? 1. So how many H's are left? 1. So how many electron regions around that carbon? I see 3 bonds and an electron. How many regions is that? 4. 4 would be what type of hybridization?
SP3.
sp3 unless something was going on. That is, would this electron like to be in a p orbital? Now if it was empty, you would say, yeah, there's a p orbital there. What about 1 electron? Well, it turns out that the same thing holds true that we said. Anytime a lone pair is next to a p orbital is going to want to be in a p orbital. Well, anytime a single electron is next to a p orbital is going to want to be in a p orbital. And so you really have, in terms of structure, 1 electron makes pi bond, but this 1 electron here is also sitting in a p orbital. And then there's no p orbital there. See, it's all over interacting. And so it really is a hybrid. And we really have bonding all through here. Now, there's no charge to talk about. The electrons are spread through here. We show that with 2 fake structures called resonance structures. Those are easy to work with. So, don't read this. What's the product here? One set captures a bromine. See, this would capture the bromine from here. It would take that bromine and cause this to become a radical. So, boom. Right there. When it captures the bromine radical. There's actually 2 possible products. What's the other possible product here?
Bromine on the edge.
Yes. This resonance structure could capture the radical. And you could actually get double bond here and bromine out there. Now we say this could capture, this could capture. Really, these are fake. This is what captures. But see, the radical character is on both carbons. It's not just sitting there, and it's not just sitting here. But either can capture the bromine radical. Again, we show this with the fake resonance structures. This is analogous to our diene chemistry when we do a HBr. We can do a 1,2 addition where the bromine adds to the cation, but then we can invoke the resonance and end up with the bromine adding over here. Okay? Now, which would you say is going to be the major product here? Which one looks more preferred? Why the first one?
Because it's also on the secondary.
But the alkenes stabilize.
But the bottom one is more stable.
More stable, yeah. It's more stable. It's disubstituted. Typically with alkenes, the alkene substitution is a big predominant factor determining stability. Unless there's something else going on that is sort of beyond the scope of what we've ever discussed. And there's plenty of other things. But believe it or not, we're only skimming the surface of organic chemistry. So NBS, anytime you see NBS, it's just bromine radical. At least in organic, introductory organic. Now, what's the next question here? I think it says, why can't you use bromine in the last example? Why not use bromine here? Megan? Because bromine would react with the pi bond to give our old alkene chemistry. Reaction with the pi bond is instantaneous. Remember when you did that in lab, it's just like almost a titration, it reacts. You can actually do that in the dark. There's no radicals there. But NBS won't add to a pi bond. Now why did bromine not add to the benzene ring? because those aren't pi bonds. Remember, benzene ring's off limits. Benzene ring doesn't react in any reactions in this class. But this is a regular alkene. The bromine could have reacted. So NBS gives you more selectivity. It doesn't react with alkenes. Here's another reason. If you had a choice of NBS or bromine, and both could work. For example, up here, you could have used NBS. You can just about always use NBS. I would have actually preferred to use NBS up here. Why might NBS be preferred to be used in terms of a practical reason, going to the lab and... What do you know about bromine in terms of its, first off, its physical state?
Gas.
Bromine's actually a liquid. It's also very volatile. You open the bottle, bromine vapors come out. You can actually see the vapors because they're hard. If you drop it, it's going to be everywhere and you're going to have to evacuate the lab. It's toxic. NBS is a nice white solid. Open it up, look at it, weigh it out. Which would you rather handle? Yeah. NBS is a white, fairly stable solid. It's not super stable because it's got that. Anytime you see these heteroatoms bonded to each other, it's usually not that stable. Nitrogen and bromine bonded together. It will undergo radical, but it's not as easy as like bromine. Why is only radical bromination? We already talked about that. Chlorination is not that selective, etc. Bromine is just a good one. Okay, why is the ability to put a bromine on an alkane so important? Okay, we made this at the top. We started from an alkane. Alkanes don't have much reactivity other than this. And actually, back in like week 3, I showed you the reaction of alkanes. It consisted of this. Look back on that handout. Or you can also react these alkanes. You can do the same reaction instead of with bromine. You can do it with oxygen. Take an alkane with oxygen, and what do you get? You get the same thing. You start putting oxygens on here. But if you use excess, you're going to put oxygens in lots of places. And you'll actually start breaking the bonds. And you'll actually start producing a lot of heat. And this is how you cook your hamburgers, because you take propane and you react it with oxygen, and it produces enough heat to have a flame, and you cook your hamburger. What's that called? It's called combustion. Okay. But it's a radical reaction. It's just an excess. Okay, it's not stoichiometry controlled. Now, in these reactions, you could do more than one bromine. We could brominate the whole thing if you use excess bromine, possibly. Bromine does tend to be selective and sluggish if it's not a good outcome. But if you react an alkane with chlorine, you're going to chlorinate the whole thing. And with fluorine, well, then you'll get some fire. Or with oxygen, if you give it enough oxygen and give it a little spark, a couple along. A little spark, like your grill with a little spark, like the spark generator. Once you light the grill, do you have to keep hitting the spark, or does it just self-propagate? Self-propagate. Okay, here's an example. Making the breast cancer drug anastrozole. We'll pick it up right here. You can look at that chemistry. It's actually an SN2 reaction up there. But let's start with number 21. What do they do to get to the final product? They reacted with benzoyl peroxide, NBS. There's a solvent, carbon tetrachloride. They're using that as solvent. good solvent. Actually, sometimes chloroform is a better solvent. But you would never use chloroform for this reaction. Why? You may abstract that hydrogen. There's no hydrogen here to abstract. That's why it's a good solvent for radical reactions. Reflux 2 hours, they do a benzylic bromination. Nice radical can form here. It can abstract the bromine from the NBS. So we get a benzylic bromination. Why is it so important to get a bromine on this carbon? So you can then turn around and take it off. But not by replacing it with an H, but by replacing it with like any nucleophile you could dream of. For example, this guy, these electrons then come in here and kick that off by SN2. We get that bond formed. And this is actually the breast cancer drug. Getting the bromine on, now you have a leaving group. And that leaving group, you can do all types of reactions with. Substitution, also do elimination. So that's actually a very fundamental starting point for creating of lots of molecules, is the radical halogenation. Because where does the original alkane come from? I mean, this had to be built, but go back to our initial example. Eventually, you had to go back and start somewhere. You can't just, okay? Like, where would this come from? It's just a hydrocarbon. Where, do you have to make that, or how is that made? Naturally. Yeah, a lot of chemicals go back to just natural products. Petroleum industry. And the petroleum industry produces lots of just alkanes. Different fractions with different boiling points, and thus they have different amounts of carbons. And there's something called petroleum fracking, and you can actually take some alkanes and you can create other ones through crazy chemistry. But from there, how do you get going? Well, this is a great way to get going. From here, well, then maybe you can create that. How would you convert that to that? Hopefully you recognize what type of chemistry that is. So here you can do all types of substitution, you can do elimination. Once you get an alkene, well, now you can do all types of alkene reactions. So it's a starting point to then going, and then it opens up, you can do anything. So that's why it's very important. A lot of textbooks usually used to start with radical reactions. Some still do. Because fundamentally it's a good starting point. Okay, we may not have much time to do this, but I want to go back. Any questions about the radical? We're pretty much out of time. Let me just introduce this. This is almost going to be just sort of a tidbit, take-home memorization. Some of you asked about this when you saw it a month and a half ago. You can look at this. If you react an alkene with HBr, what do you get? Standard Markovnikov hydrobromination. Hydrobromination. It's a standard reaction, right? How can we get the bromine to end up on the carbon on the right? Okay, look back in your alkene chapter and look at this topic. Okay, make sure you understand this. All right, we did plenty of that. How can you get to reverse regiochemistry? Okay, on Wednesday, I'd like for you to please answer this and give reagents, and then we'll briefly talk about that. But we're not going to spend much time on it. It'll just basically be a memorization reaction. Test on Monday. On Wednesday, we'll cover the other handout, which is we'll look at UV vis. And on Wednesday, which is our last day, we'll talk about the final exam. Okay, we'll meet upstairs in lab. Upstairs.